I put together a talk about 2 weeks ago for this. Then about 3, 4 days ago, I was looking through your program, and I see that there's a lot of 2D work. So I had to go back and change my talk a little bit and focus more on 2D and imaging. Of course, this is sponsored by AeroCube, so I hope you will take that away. So the talk is very different than what I was originally trying to convey to you. Okay, anyway, there are these 2 articles that would be useful. We took a lot of pain to write both these articles. They took about a year to write them, and they probably will be useful. Acknowledge a whole bunch of people, both in my groups at Berkeley, now at Rice. Professor Fert, for those of you who know Professor Fert, he's amazing guy. He's just still so very active, and so it's a lot of fun to work with him. And this person is my daughter, and she works on MBE growth of some multiferroics, and you will see some data from her work as well. And of course, acknowledge the support of the DOE program, which we're very grateful for, Army Research Office programs, and the NSF programs. Okay, the outline for this talk, as I was doing the reformulating of my talk, what I was hoping to do is to convey some of the things that have happened, for example, in CMR and those kinds of materials. This is back to late 1990s and stuff like that. The issue of competing interactions is going to be a theme throughout my talk today. Then we'll look a little bit at formation of these textures, magnetic textures, as well as the corresponding polar textures. And then last few minutes, we will talk about energy efficient computing. I will take you through some of those questions as well. Okay, so the first example, there are a few examples in the beginning, just to show you how, you guys know these systems very well. The 2D materials are all very well known to this community. The one example that we've been working on for about 4 or 5 years now is this iron germanium tellurium system. It's formally a 2D kind of a system. The bonds in between the tellurium atoms are relatively weak, so it behaves very much like a 2D system. The interesting thing in this system is that as you start to put cobalt into the system, it goes through a series of phase transformations. At 0% cobalt, it has this centrosymmetric ABC structure. All the way up to about 50% cobalt, it is centrosymmetric in the so-called AA structure. But right at 50%, it starts to go into this AA prime structure, which breaks inversion symmetry. And these materials are ferromagnetic with the TC well above room temperature. They also break inversion symmetry. Formally, they're multiferroics. Of course, these are metallic systems. So these are formally polar metallic ferromagnets. Okay. Now, if you look at the atomic structure, there's just some beautiful electron microscopy. I know this is a different kind of imaging group, but I'm formally an electron microscopist. This is work done by David Miller and Yutsen Shao at Cornell. You could actually image the atomic structure of the AA phase, and you could see it forms this zig structure. And you can go into the individual atomic positions. We have the resolution now to do all of this, and this pointer is busted. We shall see. Nope, we will use this. Switch it on. Good. All right, if you look at this structure, you have to look at it a little bit carefully. It has a structure which has the zig structure. And it also has the 7-atom sequence. Essentially, it's all completely 7 atoms. And so you can clearly see that there is a mirror plane in this system. There's no broken inversion symmetry. At the 50% cobalt doping, you can see it goes into this green, blue, the zigzag structure. At the same time, it goes from 7 layers to basically 6-layer sequence. And you automatically know there is something that's breaking symmetry there. So in this particular system, you can follow the broken inversion symmetry at the atomic scale. So the key question is, why is it that putting cobalt into the system breaks the symmetry? Now, there's a lot of electronic structure calculations that's happening, but we don't have conclusive proof yet as to why the system goes into that phase. Oh, let's use the old-fashioned way. Now, at the 50% composition, you start to see the formation of nail-type skyrmions. These are MFM images. You can capture exactly the same with Lorentz stem images as well. These are the stem images. These are the reconstruction of the B field of the skyrmion, and the actual schematic is shown like so. These are nail-type skyrmions. Okay, only in the AA phase. So the broken inversion symmetry is incredibly important for the formation of these magnetic textures. And accompanying that, you could also see the topological Hall effect. This was a very difficult experiment. It took us a while to get this done. And this just tells you the various contributions to the measurement, the resistances, the Hall, the anomalous Hall effect, and the topological Hall effect. And that is because of this topological electric field that you create. And the motion of the electron through this skyrmion leads to a drift in one direction because of this emergent electric field. Now, as you apply a current to this, you can start to move the skyrmions, and you can start to see that the resistivity or the resistance contribution to the topological Hall effect keeps coming down. It's a very small value. It's not a huge value, so you have to really do it carefully. Those skyrmions begin to move at about 1.4 or so mega amps per centimeter squared, and then they start to move, and this resistivity contribution comes down. So those are all evidences that you can actually have the skyrmions tuned by the structure, and then you can start to do dynamics with them. A related system is the iron gallium tellurium, but the origin here is a little bit different, but not dramatically. In this case, the original compound, if X is 0, it's quite boring. But if you start to intercalate X, which is iron, into those lattice, and you can actually pick up that intercalation in these atomic resolution images. That's right there, that there's intercalation of iron, not very uniform, but it is there. That leads to, again, a very interesting magnetic state. There is competition between multiple phases. You can follow that intercalated site quite easily through these images. Keep in mind that these images are projected through the thickness of the sample, which is maybe 10, 20 nanometers or so. Okay? And these are the bigger scale images of the atomic structure. Now, if you look at schematically, those are three different phases: the ferromagnetic phase, which is the moments in the layers and the intercalated layer. Or it could be ferromagnetic-like, where this could be antiferromagnetic, but that moment is smaller compared to the main moment. Or it could be purely antiferromagnetic-like. Now, all of them are competing. They're not dramatically different in energy scale, so they're competing with each other. So if you look at Lorentz images of this is the 4D stem Lorentz image, you can actually see the coexistence of these two phases. One of them is the so-called ferromagnetic phase, in quotes. The other one is this ferromagnetic phase, which is more like this. And so they can coexist. You can go back and forth between them. So it's telling you that at the local scale, you could have chemically driven competition. Going away from metallic systems, we're not going to spend a few minutes on insulating systems. This is the case of a ferroelectric material, very canonical system, lead titanate. Okay? So if you look at the classical thermodynamics of the system, it has a double well structure, which is shown here. And it's always been thought that this position, the end point, is not stable. And that's true. That's absolutely true. But if you now create a structure which has very different behavior, then that may not be true. This is what I'm going to take you through in the next few minutes. So what we're going to do is to use epitaxy to create competing energy scales. And that leads to the formation of both vortices and skyrmions. These are not magnetic skyrmions, so the origin is slightly different. Unlike in magnetism, in ferroelectrics, the lattice plays a very strong role. In most magnets, it does not play a big role. And it leads to a lot of very interesting new things, which I'll show you in just a second. Okay. All right, so I'm capturing 8 years worth of work in a single slide. Oh, okay. So what we can do, we now have the power of epitaxy. Either by MBE or poor people like myself, we use pulse laser deposition. But you now have the ability to grow materials essentially unit cell by unit cell. Darrell Sloan at Cornell does some beautiful MBE. But what you're really doing is taking a material like lead titanate, putting strontium titanate, which are sister compounds. They're all perovskites, essentially the same lattice parameter. And you can start to build them very much like building an apartment complex outside. And you can see these are the super lattices. In this case, 10 unit cells of lead titanate. You can see the brighter contrast. Lead is a bigger atom, so you see that. And 10 units of strontium titanate. Now, if you look at it with a little bit more care, which means you start to do detailed analysis of the atomic position, what you see is that the lead ions, or the titanium ions for that matter, are not fixed. They're actually spiraling. Not that they're moving around, but they're spiraling in space. Okay? And that's shown here in this part. This is called a vector map. And you can see that those form vortex-like structures. If you now look at it from the top, it doesn't look like any classical ferroelectric. Jan Seidel has done enormous amount of work through his life. It doesn't look like lead titanate at all. It looks very much like carbon nanotubes. Each one of these tubes is one of these vortex core. So these look like cigarettes in some sense, nanoscale cigarettes. I'm going to come back to this picture in just a second. Now, with epitaxy, what you can do is to impose polar gradients, like in lead titanate, strontium titanate, elastic gradients, dielectric gradients, and so on. So you now have a framework, a pathway by which you can create a lot of new structures. You can take other such systems like bismuth ferrite or any other ferroelectric or any other material, start to create these emergent textures. Now, the physics is embedded here. If you look at the Hamiltonian for this, there are two terms, the elastic energy and the electrostatic energy. I'm going to spend just 10 seconds explaining that to you. Now, in a case of a ferroelectric, which is not true in most ferromagnets, except maybe in rare earth ferromagnets and stuff, in a ferroelectric, the spontaneous dipole is coupled to the lattice. So people will tell you that barium titanate is tetragonal, bismuth ferrite is rhombohedral. So if you impose boundary conditions like you do here in the polar gradient, then the system is saying, I have a very large polarization, I might as well put it in plane. Okay? And so if I impose this kind of a boundary condition, the implicit answer is put the polarization vector in plane. But it can't do that because it's stuck to a substrate. And therefore, when you start to stretch the lattice, it says, I can't do that because this term begins to dominate. So if you have the elastic and the electrostatic terms of approximately the same, meaning you have competition between them, you start to get these emergent textures. Okay? And so you could also see on this picture, these vortices have interesting defects. And this is really going back to the stability, the thermodynamics of 1D and 2D lattices. A lot has been done on this. There have been fantastic amount of work done in the superconductivity area. But if you look at these smiley faces, I'm not sure if you can see it from the back. These are the smiley faces, but some of them are up, some of them are inverted. They correspond to pairs of dislocations. So if you go back and look at old theories, or even the Castells-Thouless idea, the whole phase transition is being mediated by the formation of topological defects, like a dislocation. So indeed, you can image those dislocations. So the question is, can we get a perfectly ordered 1D lattice of these vortices, or is it always going to be defective? Nobody knows that. So it's a huge opportunity for research. Okay, now I'm only going to give one slide on this. Lot of interesting new physics happens. We've spent the last 8 years, 10 years on that topic. That review article I mentioned captures everything. If there's one article, that's the one. We see effects of negative capacitance. It's a very controversial topic because negative capacitance is supposed to be impossible in equilibrium, and that's true. But if you look at the dielectric permittivity of these superlattices, they are about 800. Lead titanate is about 50 to 70. Strontium titanate is about 120. So if you have layers of lead titanate and strontium titanate in series, you expect that the effective permittivity should be here, this black line. No, it's actually 20 times larger. That happens because in these systems, the vortex core is actually sitting at the peak of the double well structure, not at the valley of the double well structure. And therefore, in local regions, there's nothing that says that you cannot trap in regions of negative permittivity. Permittivity being negative, meaning the curvature or the second derivative of the free energy, is negative. It can happen on local regions, not over the entire volume of the material. Okay? So you can trap in negative permittivity and get large effects on that. You also have handed behavior. You take two materials, lead titanate and strontium titanate. Neither one of them is chiral. You put them together in a certain way and get these vortex or skyrmion-like structures. You can start to pick up handed behavior. This is resonant soft X-ray diffraction. The LBL people have been fantastic in doing this work. They helped us a lot. And you can start to see circular dichroism in those measurements. Typically, circular dichroism is because of natural optical activity, or if you have ferromagnetism. This material effectively behaves like a ferromagnet. It's not a ferromagnet. It behaves like a ferromagnet. And you can switch that chirality with an electric field back and forth. You can now start to do it with second harmonic measurements, near-field measurements, and so on. The third part of it is collective dynamics. These vortices, when you hit them with ultra-fast light pulses, they will start to go into collective oscillations. And in this paper, this Nature paper from Argonne, they call it a vortexon. It's a quantum of these collective oscillations. So a lot of new things happen in this system. Coming to a favorite system for myself, in the case of bismuth ferrite, which is a multiferroic material, which is a very fascinating system from the physics perspective. If you look at it, it's got a very large polarization along the 1-1-1 direction. That's the P vector. It's antiferromagnetic, so you have ferromagnetic planes along the 1-1-1 direction, but which are coupled anti-ferromagnetically, which is these two vectors. Now, there are two things on top of this which make it very interesting. The first thing is, because of this Dylogzinski-Moria interaction, there's a small canting of these antiferromagnetic planes. It's a very small amount, about 5 EMU per cc. Okay. And that canting is very important, turns out, for many different things. Okay. So if you now look at this schematically, that's the polarization direction. That spin, the canted moment, is not uniform in the bulk. In thin films, it can change, but in the bulk, it's not uniform. But it also couples to the spontaneous polarization, and therefore, it starts to spiral around. And we call it a spin cycloid. Okay? Now, there are two interactions I mentioned. One is the coupling to the polarization. The second one is formally called the Lifshitz invariant. It's coming up because of the octahedral tilts in this system. Sum and substance of this, you see this kind of a cycloid-like behavior of the magnetic moment. Now, until a few years ago, this now comes to imaging, and the next few sets of images are just, in my mind, mind-blowing. It's fantastic. It comes about because of the imaging capability. Of course, this is one of your competition. This is Kunami, and what's the name? Amiri Kobi from Harvard did a lot of the pioneering work on this topic. So you can use an NV diamond to map out the magnetic structure. The good news is it's about 2 to 3 orders more resolution than an MFM. So this paper is a beautiful paper from the folks in Thales, where they imaged the spin cycloid. This is the cycloid itself. The spacing is about 65 nanometers using the NV system. That's the cycloid that they were imaging. And it turns out that it's so good, we started collaborating with people. And it became so exciting that we said, we need to go buy one of these. And indeed, we do have one of that in our lab. It's a very specific piece of instrument. It's very sensitive, but you can get some amazing, amazing images. These are images of the spin cycloid in bismuth ferrite, where you have an array of 71-degree ferroelectric domains, and you can see it forms beautiful ordered structures of the spin cycloid. You can start to see defects in the spin cycloid. You can start to see dislocations. If I now grow this on a 1-1-1 surface, where the polarization vector is coming out of the plane, then you can start to see what we call Turing patterns. These are the spiraling patterns of the spin cycloid. This is literally 3 weeks old data, so we are still trying to figure out what all of this means. But basically, I have enough stuff to quit all of the monkey business I'm doing and go back full-time to research, which I am planning to do. So it's just fantastic what these imaging techniques can do. So thank you to AdaCube and to Kunami and everybody else who has been putting on this. Okay, I want to show you a piece of data which this kid, who happens to be my daughter as well, Using epitaxy, you can control the ferroelectric domain structure as well as a spin cycloid. And that's the set of data I'm going to show you. Now, if you grow bismuth ferrite on dysprosium scandate, which is about 0.8% mismatched to the bismuth ferrite, you start to see this very nice ferroelastic twin-like structure. We call them 71-degree domains. If I go to a sister substrate, terbium scandate, which is only 0.1% mismatched, you start to see not 71, but 109-degree domains. Mainly because electrostatics dominates here, while elastic energy dominates here. If you now go back to exactly the same samples and do the NV imaging, you can start to see the chevron-like pattern, while for the terbium scandate, it forms a single variant, almost like a lattice. And that single variant has the cycloid that looks like a plane wave. If you go along this direction, which is direction 1, you can see that the green arrows are approximately all in the up direction. While you go this way, the green arrows are going up, down, up, down, up, down. Okay. And so you can actually start to create a lattice, a reasonably ordered lattice of the spin cycloid. And that's shown here in this image. It took a while. It took about 2 weeks to get this image. It's a 10-micron scan of this lattice. And you can see that it's essentially 1D lattice. But if you focus hard enough, you can start to see dislocations in that. It looks almost exactly the parallel universe of the vortex lattice that I showed you maybe 5 minutes ago. There are defects in the lattice, so the questions are the same. Can you ever get a perfectly ordered vortex lattice? Or in this case, a cycloid lattice. How about phase transitions in the cycloid lattice? So you can now start to create model systems where you can look at this very carefully. If you do transport parallel and perpendicular to these cycloids, you see a very large anisotropy in spin transport, which I'm going to focus on in the last 10. How much time do I have? Another 10? Perfect. That's 1 or 0 or 10? Yeah, 10. Okay, fine. Yeah. If you measure spin transport, I'm going to get into the details of the spin transport in just a second. If you do spin transport through them simply by launching spins through the system, in this case, you would have magnons in the multiferroic. There is a very large anisotropy parallel and perpendicular to these cycloids. Okay? So you can now start to probe transport of spins through these tubes of cycloids in the system. If I do the same experiment for the zigzag or the chevron pattern on dysprosium scandate, you see no anisotropy. So you can now start to use pathways like this to create a band gap, for example, in the magnon spectrum of these systems and start to probe them. You can manipulate them with an electric field and so on. Okay. Now we come to the main topic that I proposed to Mirko in the abstract, which has to do with energy efficient computing. I still wanted to be true to what I had told you about. So taking you back, this is the talk I had set up would have gone into global macroeconomics. You guys would have died because you're all physicists, but that has to do with the scale of markets. You know, the market is going to be maybe $2 trillion by 2030. And it's huge competitiveness. There's a lot of other things that go on. But if you look at the entire game in a very simple way, this is the picture that shows you the MOSFET for a silicon and the energetics of that. This kT log 10 divided by the charge of the electron equals 60 millivolts simply comes from Boltzmann distribution function. That governs the transport of the electron under an electric field where you apply the field to it. This is also called the Boltzmann tyranny because that's the best that you can do for a silicon channel. So in the last 10 years or so, a bunch of people, including ourselves, we've been saying, is there any other way to play the game? Do I have to deal with uncorrelated electrons? Is there a pathway where we can use spontaneous dipoles in a ferroelectric, or spins, ordered spins in a ferromagnet, or even correlated electron systems, for example, to overcome this tyranny? Indeed, it looks like you can, but how to do that? So in doing so, you will go from a total dissipation in a single switching event of nkt log 2, which is simply the change in the entropy of the system as you apply the electric field and switch it. Okay? It goes from nkt log 2 to simply kt log 2. That n goes away because if you have n particles, they're all internally correlated by exchange interactions or dipolar interactions and so on. Okay? So in doing so, the question that we were asking is, and it's going to impact everybody because of a few simple things. AI, machine learning is going to take off. It's already taking off. IoT is going to take off. Things like what Atocube are building are going to be very computing intensive. Okay? So the question is, can you make computing 1,000 times more efficient? Today it's about maybe 20 picojoules per operation. Can we go down to femtojoules? In our case, we want to go to attojoules. So appropriately for Atocube, we want to do it at 1 attojoule per operation. Now, it's not impossible. It's still not the Landauer limit. It's still far from the Landauer limit. It's of the order of 100 kT. So we could use ferromagnets, ferroelectrics, order parameters in some sense to do this. Okay? The other thing from a systems level is that if you look at how your computer is structured, it has a logic sitting here, manufactured wherever in TSMC or Intel, and the memory sitting here. They're actually two different chips. This guy, whenever it works, is doing both of them together. So the question that we've been asking is, can we do logic and memory? Or if you talk to electrical engineering colleagues, they will talk about in-memory compute. Okay? Which means I use a memory, a bistable system for memory. In the off state, it is simply a memory. But when it's working, it's doing logic with that. And that's easier said than done. How does one go about doing it? So about 8 years ago, with our Intel colleagues, we proposed a crazy new device called the MISO, magnetoelectric spin orbit coupled device. Input a charge into it. The magnetoelectric layer converts it to a spin. You do all the logic operations there, and you read it out as a charge signal, because it's much more easier to read out a charge signal. Not easy to read out a spin signal, unless you do optics or something. But the biggest learning in all of this is that for a materials person like me, is that voltage equals energy. Okay, that's relatively straightforward. 1/2 CV squared is what we've been taught in our classes. So our goal is to get to very low voltages. Ideally, we want to get to 100 millivolts, and then to 10 millivolts, and so on and so forth. Okay. So the challenges for quantum materials, this entire community. Can you convert charge to spin at 100 millivolts? I'll show you data in a second. That's possible. Can you convert spin to charge at 100 millivolts? That's very difficult. That's not easy. So I'm going to show you some data as I finish up my talk. Okay, now on the microscopic scale, I showed you this example before with bismuth ferrite. These are the spin spirals. When you apply an electric field to this system, you can actually switch it back and forth. You can microscopically see electric field control of magnetism. When Jan Seidel and a whole bunch of people were in our group, they actually did some beautiful experiments using photoemission-based stuff, linear dichroism. But now you can do all of this with imaging on the very microscopic scale. So we know that you can control magnetism with an electric field. You can put a spin valve on top of this, and you can actually measure that and prove that you can switch magnetism at 500 millivolts with an electric field. These are photoemission-based or XMCD-based measurements. Can we get below 100 millivolts? It's a challenge. Okay, the challenges are captured on this slide. We have to be able to manipulate the double well structure. You have to really pay attention to every atom. In the case of electric field, we're looking at very small thicknesses, maybe 3 to 5 nanometers. How do you make perfect materials? How do you overcome mechanics of the ferroelectric? We know that we can get to about 200 millivolt switching, but we need to get to much lower voltages. Okay, I seem to be running out of time. I want to spend maybe 2 minutes. Is that okay? Yes? Okay, all right. So the spin orbit part, I wanted to show you some examples. This is really, in my mind, a place where we used to think, oh, getting beyond 100 nanovolts is very difficult. I want to show you, no, that's absolutely possible. So let me go to the last slide, and then you can ask me questions later. So I want to show you a piece of data where we have a spin orbit metal, Not platinum or tungsten, which is the metal that everybody has been looking at, but these are correlated metals. These are metals like strontium iridate or barium lead bismuth oxide. Strontium iridate behaves very much like a topological insulator. So we've been doing spin Hall and spin Seebeck measurements. And this is the essential data. So these red stripes are basically the metal layers, strontium iridate, where we do the spin Hall measurement. And what you can see is that compared to platinum, which is this open squares, the black one, and tungsten, the spin Hall angle is about 10 times larger for the strontium iridate compared to platinum. We think it can be significantly larger than that as well. Nobody knows the limits of these. We can switch that with an electric field. The red data is the ferroelectricity, and the blue data is the corresponding spin Hall switching. So you can switch it back and forth, and as you can see, it's significantly larger than platinum. And this data is what is exciting, but it's also very rudimentary, very early stage. You have to take it with that spirit. What you plot here is the output voltage as a function of the spacing. And going down to about 10 nanometers, which is kind of like a vertical structure, we think we can get to 10 millivolts output. This is the spin Hall voltage. But it's measured in a very careful way. You cannot do DC because of leakage issues. So you have to do a resonance-based measurement. But the message I wanted to give you is, by making these perfect materials, indeed, it may be possible to get to numbers like this, which then comes to devices which are shown schematically here, where you can have a very simple capacitor-like structure. I can manipulate the magnetism. I can read out the changes in the magnetism with the inverse spin Hall voltage. That spin Hall voltage is now approaching a millivolt, not 100 nanovolts, but 1 millivolt. And we think with some tuning, this is a 100 nanometer thick sample. Going down to 10 nanometers, doing very careful measurements, we should be able to get of those. Now, the big question that we don't know the answer to is, can you do logic with this? We think we can do memory with this, but logic is a lot more difficult. So let me summarize with this one slide. This is the essence of what I've talked about in the last 10, 15 minutes. We can create perfect materials with epitaxy, where you have the spin orbit coupled oxide, the multiferroic, which has a spin and the dipolar degrees of freedom, and pick it up there. What are the challenges? Scaling clearly is a challenge. Can you go down to a few nanometers? How do you measure them? Spin to charge conversion, what are the limits on those? There's no thermodynamic limit established so far. Can we get spin Hall angles of 50, for example? Is it even possible? What do I need to do to get to that? We know that we need to tune the electronic structure. The band structure is very important. So the key is to make perfect materials, perfect interfaces. Having tools like what AttoCube and Qnami make is absolutely essential for this. So thank you very much for the chance to speak. Happy to take questions.
Thank you for the fantastic talk. Any question from audience?
So the meso idea certainly is very exciting. And how far away from realization of the meso in real devices?
Yeah, this is a great question, isn't it? We spend a lot of sleepless nights on this. Our friends in Intel are pursuing it with great intensity. We ourselves are doing it. The ferroelectric part is at least 3 orders of magnitude, a lot more advanced. There are startup companies, advanced companies which are doing it. But doing the spin part and the charge part together is not trivial. It's only going to work if you have the ability to get very large output voltages. Now, if you look at the meso structure, there was a ferromagnet. In this structure, there is no ferromagnet. We got rid of it because you're now reading out the antiferromagnet directly. And that's relatively new. Actually, we are seriously thinking of doing a startup company on this because we think we can get to these kinds of numbers. We've still got some work to do.